Praseodymium is a chemical element with symbol Pr and atomic number 59. Praseodymium is a soft, silvery, malleable and ductile metal in the lanthanide group. It is valued for its magnetic, electrical, chemical, and optical properties. It is too reactive to be found in native form, and when artificially prepared, it slowly develops a green oxide coating. The element was named for the color of its primary oxide. In 1841, Swedish chemist Carl Gustav Mosander extracted a rare earth oxide residue he called didymium from a residue he called lanthanide, in turn separated from cerium salts. In 1885, the Austrian chemist Baron Carl von Welsbach separated didymium into two salts of different colors, which he named praseodymium and neodymium. The name praseodymium comes from the Greek prasenos, meaning green, and didymos, twin. Like most rare earth elements, praseodymium most readily forms trivalent Pr ions. These are yellow-green in water solution and various shades of yellow-green when incorporated into glasses. Many of praseodymium's industrial uses involve its use to filter yellow light from light sources. Characteristics. Physical properties. Praseodymium is a soft, silvery, malleable, and ductile metal in the lanthanide group. It is somewhat more resistant to corrosion in air than europium, lanthanum, cerium, or neodymium, but it does develop a green oxide coating that spalls off when exposed to air, exposing more metal to oxidation. A centimeter-sized sample of Pr completely oxidizes within a year. For this reason, praseodymium is usually stored under a light mineral oil or sealed in glass. Unlike other rare earth metals, which show antiferromagnetic or and ferromagnetic ordering at low temperatures, Pr is paramagnetic at any temperature above 1 K. Chemical properties. Praseodymium metal tarnishes slowly in air and burns readily at 150 degrees Celsius to form praseodymium oxide. 12 Pr plus 11022 Pr 6011. Praseodymium is quite electropositive and reacts slowly with cold water and quite quickly with hot water to form praseodymium hydroxide. 2 Pr plus 6H2O2 Pr 3 plus 3H2. Praseodymium metal reacts with all the halogens. 2 Pr plus 3Fu2 PrF3. 2 Pr plus 3Cl2 2 Pr Cl3 2 Pr plus 3 Br2 2 Pr Br3 2 Pr plus 3I2 2 Pre3. Praseodymium dissolves readily in dilute sulfuric acid to form solutions containing green Pr ions, which exist as a 3+ complexes. 2 Pr plus 3H2SO4 2 Pr 3 plus 3SO2 minus 4 plus 3H2 compounds in its compounds. Praseodymium occurs in oxidation states +2, +3, +4, and uniquely among the lanthanides, +5. Praseodymium is a strong oxidant, instantly oxidizing water to elemental oxygen, or hydrochloric acid to elemental chlorine. Thus, in aqueous solution, only the +3 oxidation state is encountered. Praseodymium salts are yellow-green and, in solution, present a fairly simple absorption spectrum in the visible region, with a band in the yellow-orange at 589 to 590 nanometers, and 3 bands in the blue-violet region at 444, 468, and 482 nanometers, approximately. These positions vary slightly with the counter-ion. Praseodymium oxide, as obtained by the ignition of salts such as the oxalator carbonate in air, is essentially black in color and contains +3 and +4 praseodymium in a somewhat variable ratio, depending upon the conditions of formation. Its formula is conventionally rendered as Pr 6011. Although praseodymium in the bulk state is unknown, the existence of praseodymium in its +5 oxidation state under noble gas matrix isolation conditions was reported in 2016. The species assigned to the +5 state were identified as +Its O2 and R ducts, and Pro2. Other praseodymium compounds include fluorides PRF2, PRF3, PRF4, chlorides PrCl3, bromides PrBr3, PR2Br5, iodides Pre2, Pre3, PR2I5, oxides Pro2, PR2O3, PR6011, sulfides PRS, PR2S3, sulfates PR23, selenides PRSE, tellurides PRTE, PR2Te3, nitrides PRN, carbonates PR23. Isotopes. Naturally occurring praseodymium is composed of one stable isotope, praseodymium-141, which is of use in NMR and EPR spectroscopy. 38 radioisotopes have been characterized, with the most stable being praseodymium-143 with a half-life of 13.57 days and praseodymium-142 with a half-life of 19.12 hours. All of the remaining radioactive isotopes have half-lives that are less than 6 hours, and the majority of these have half-lives that are less than 10 minutes. This element also has 15 nuclear isomers, with the longest-lived being praseodymium-138 meters, praseodymium-134 meters, and praseodymium-142 meters. The nuclei of nuclear isomers exist in a delicate equilibrium and metastability due to at least one nucleon having an excited energy state. The isotopes of praseodymium range in mass number from 121 to 159. The most common decay mode of 20 isotopes with mass numbers lower than the most abundant stable isotope, praseodymium-141, is beta plus decay, primarily forming serum isotopes as decay products. The most common decay mode for 18 isotopes with mass numbers higher than praseodymium-141 is beta minus decay, primarily forming neodymium isotopes as decay products. History. In 1839 Mosander extracted an oxide he called lanthanide, which was the oxide of the newly discovered element lanthanum, from a mixture of crude cerium nitrate. In 1841, Mosander went on to show that lanthanide was the most strongly basic of a mixture of rare earth element oxides and was the last to be precipitated from acid solution when base was added, or the first to be dissolved when the mixed oxides were leached with dilute acid. The remaining less basic rare earths retained the pinkish color, and Mosander called this remaining fraction didymium. In 1874, Theodore Cleve concluded that didymium was in fact two elements, and in 1879, Lecoq Du Bois-Baudran isolated a new earth, samarium, from didymium obtained from the mineral samarskite. Crude didymium actually contained 3 elements, and in 1885, the Austrian chemist Baron Carl von Welsbach separated didymium into 2 elements, praseodymium and neodymium, which gave salts of different colors. The name praseodymium comes from the Greek prasenos, meaning green, and didymos, twin. Praseodymium is frequently misspelled as praseodymium. Leo Moser investigated the use of praseodymium in glass coloration in the late 1920s. The result was a yellow-green glass given the name Praseodymium. However, a similar color could be achieved with colorants costing only a minute fraction of what praseodymium cost in the late 1920s, such that the color was not popular. Few pieces were made, and examples are now extremely rare. Moser also blended reacted praseodymium with neodymium to produce heliolite glass, which was more widely accepted. The first enduring commercial use of purified praseodymium, which continues today, is in the form of a yellow-orange stain for ceramics. Praseodymium yellow, which is a solid solution of praseodymium in the zirconium silicate lattice. This stain has no hint of green in it. By contrast, at sufficiently higher loadings, praseodymium glass is distinctly green, rather than pure yellow. Using classical separation methods, praseodymium was always difficult to purify, much less abundant than the lanthanide and neodymium from which it was being separated. Praseodymium ended up being dispersed among a large number of fractions, and the resulting yields of purified material were low. Praseodymium has historically been a rare earth whose supply has exceeded demand. This has occasionally led to its being offered more cheaply than the far more abundant neodymium. Unwanted as such, much praseodymium has been marketed as a mixture with lanthanide and cerium, or LCP, for the first letters of each of the constituents, for use in replacing the traditional lanthanide mixtures that were inexpensively made from monazite or bastnasite. LCP is what remains of such mixtures, after the desirable neodymium, and all the heavier, rarer, and more valuable lanthanides have been removed by solvent extraction. However, as technology progresses, it has been found that praseodymium can be incorporated into neodymium iron boron magnets, thereby extending the supply of the much in-demand neodymium. So LC is starting to replace LCP as a result. In the 1930s it was found that praseodymium dioxide could be precipitated from sodium hydroxide eutectic melts, by oxidation by electrochemistry, or by sodium chlorate. This formed the basis of a small-scale laboratory purification method. The relatively pure free metal itself was not prepared until 1931. Occurrence: praseodymium occurs in small quantities in Earth's crust. It is found in the rare earth minerals monazite and bastnasite, typically comprising about 5% of the lanthanides contained therein, and can be recovered from these minerals by an ion exchange process, or by countercurrent solvent extraction. Mischmetal, used in making cigarette lighters, historically contained about 5% praseodymium metal. Praseodymium makes up an average of 8 parts per million of soil's dry weight, though the element's concentration there can be as low as 1 part per million or as high as 15 parts per million. Praseodymium makes up 1 part per trillion of seawater. There is almost no praseodymium in the atmosphere. Applications: uses of praseodymium in combination with neodymium, another rare earth element. Praseodymium is used to create high-power magnets notable for the strength and durability, as an alloying agent with magnesium to create high-strength metals that are used in aircraft engines. Praseodymium makes up 5% of the traditional version of mischmetal. Praseodymium is present in the rare earth mixture whose fluoride forms the core of carbonatolites, which are used in the motion picture industry, for studio lighting and projector lights. Praseodymium compounds give glasses and enamels a yellow color. Praseodymium is used to color cubic zirconia yellow-green, to simulate the mineral peridot. Praseodymium is a component of didymium glass, which is used to make certain types of welders and glass blowers goggles. Silicate crystals doped with praseodymium ions have been used to slow a light pulse down to a few hundred meters per second. Praseodymium alloyed with nickel has such a strong magnetic caloric effect that it has allowed scientists to approach within 1/1000th of a degree of absolute zero. Doping praseodymium in fluoride glass allows it to be used as a single-mode fiber optical amplifier. Praseodymium oxide in solid solution with ceria or with ceria zirconia have been used as oxidation catalysts. Modern ferrocerium fire steel products, commonly referred to as flint, though having a completely different chemical composition to naturally occurring flint rocks, used in lighters, torch strikers, flint and steel, fire starters, etc., contain around 4% praseodymium. Precautions: like all rare earth metals, praseodymium is of low to moderate toxicity. Praseodymium has no known biological role.